Okay, so we're going to switch to cadence now, and here we have our signal path, and then the assumption at this point is that we have already worked the size of this device and the bias this device is needed to handle noise and linearity requirements. We also place the right feedback that we need, the size of the resistor, so that we accomplish the gain that we need, and also that it has the noise requirements that we need, and we did some compensation. So for completeness, I'm going just to run one very quick simulation here. So I'm going to use the ADXL, and the idea is that basically the same simulation results that I have in my small signal path have to be exactly the same or extremely similar to the ones that I have when I simulate the bias circuit. So I will do a quick simulation with ADXL, and so this is a transimpedance amplifier with a 100 kilo ohm gain. So what we have here is that the closed loop gain, it is around 94 kilo ohms, and after compensation we place the poles in Butterworth positions, around Butterworth positions. So you can see the root locus. We started here, and then with this capacitor in the feedback, I move the poles to Butterworth positions. And it's a single stage, so it has limited loop gain around let's see, what is the loop gain? Loop gain is here. The loop gain is around 36, so this is what I can expect for a single stage. Okay, so we have this information, and let's assume for a second that we are happy with this amplifier as it is, and now it is time to do the biasing. So the first thing that we should do now, it is just to replace this small signal model with a bias transistor, and then I go to so I have replaced that the small signal model with the transistor and the current source, the IDS current source, VDS current source, and VGS current source that I extracted this information, the VGS from the previously from the DC operating point, from the DC bias that we ran before, and now our objective here will be to move these voltage sources and manipulate and or transform this current source, so that at the end of the day we will only have this VDD power supply left. So before this, I will run now a simulation here. So for these quick simulations, we really don't need ADXL. We can have it something very simple with ADE, because we just need to check the operating point and run some basic AC simulations very quick, just to verify that when we do the merging of the sources of moving sources, we don't do any mistake, so we don't need something really advanced. So we're going to get some DC operating point, and actually at this point, when I have the transistor already connected here with the right VGS, right current, and right VDS here, I can already run noise simulation, pulse zero simulation, AC simulation, and DC sweep. So I can have already a first simulation of static nonlinearity. So I can test here the static nonlinearity. So in this particular case, I am sweeping the input from -10 micro to 10 micro. Okay, and see how the output voltage changes. So we are going to run this one, run the simulation, and then this is what we get. So let's see first the gain. The gain, it is 94.7. It's exactly what I expected from the small signal model. So it has to be exactly the same. It has to be exactly the same. Maybe the pulse will change very little because we didn't extract all the capacitances. So there is some change in the pole positions here, but typically this has to be very similar, if not the same. Then we have this is the output after the DC sweep of the input, and I can derivate this curve in order to get the differential gain, and then I can already calculate the differential error here and run linearity performance test, basically harmonic, checking the second and third order harmonic distortion and see if it is under specifications. If it is not under specification here, we have to stop because it's not going to get better when we finish the biasing. So we should check here if whenever it's possible, we should check here if it is the linearity of the system. It is under specifications. Okay, and finally, what I will do here, it is we can just upload annotate DC voltages, and we can also do it from here. Operating points. And then we can see results from here, annotate DC operating points. We can see here that the transistor is sinking the 20 microamps that I put in this current source, and that yeah, look, there is 0 volts here. So the sources that I place basically remove the offsets. So I load, any load that I put here is going to be close to 0 volts. The same at the input. The input I have 21 microvolts. So the offset, the DC source that I put at the input, it just remove the offset. So this node, it is around 0 volts. So it is very nice because it has removed all the offsets, and then it has biased this transistor. So then we are right here now. We're going to start moving these sources. So we can close this one. So the first thing that we do is, yeah, we have done already this test, DC operating point, AC noise, pulse zero, static nonlinearity, and then we start moving the sources. And then the first thing that I did was move BGS1 and BDS. Okay, so originally we have BDS. We had a BDS here. I will move this one in this direction and in this direction, and that is what I have done here. Okay, that has been moved there, and then I will move this one in this direction also, so it cannot enter here because this is a capacitor. It's an open circuit for DC, so this has been moved here. So now look at this. These are in series. These two sources are now in series. Now the second thing that I do in this circuit is that I transform my DS1 into two sources. So IDS1, it is here. So I transform into sources. So these two sources. This current source that was connected to ground, okay, now it is connected to VDD, and then I have the same current coming from VDD to the drain of the transistor. So I transformed one current source to two current sources. Yeah. So yeah, in this point I stop. Okay, so I did this transformation and then I run a test. I always need to test in case I made some mistake. So let's open the circuit, and then again we just run the very quick validation to make sure that we didn't make any mistake. So I'm going we can run it directly from here. And then where we have it is here. So it has not changed from what we had before. We have the same behavior for the sweep, the same behavior for the AC gain, and then the position of the poles are the same as before, and noise also is the same. So I double check with the operating points to make sure that the transistor is biased correctly. So we go to DC operating points and DC node voltages, and then we can see that the transistor has 900 millivolts VDS and it's sinking 20 microamps, so nothing has changed in the biasing. Okay, so now we can close this one. We can close this one, and then we go to the next step. Now, first there is a current source that is in parallel to VDD. So it's basically this one here. Let's change it to green. So this one here, it is parallel to VDD. So this has nothing to do with my circuit anymore. This is a current source that it is in parallel to VDD. So I can already delete this current source. It is not really connected to my circuit anymore. So I can delete this one. So I remove that one. Now we have to. Now it is time to check if we can reuse the feedback loop. Okay, the feedback loop, and to do that, I will remove the voltage sources that are here in series, and then I will let the feedback to correct for them. Remember that this is a negative feedback system. It is supposed to correct itself, so that the output only depends on the input and in the feedback component. So when I add this voltage in the feedback loop, inside the loop, it will try to correct itself. So if I remove them, it will also try to correct for those. So I will remove them. So I remove this voltage source here and this voltage source here, and then I will check if it can correct itself. I have one remaining voltage here, this voltage here. This one I will replace by a capacitor, and here I need really to check if my source can tolerate DC voltage and currents or not. For instance, if it is a reverse bias diode, there must probably be the need to put reverse bias voltage here, and then it will need to be connected. But it might be that there is another kind of source that cannot be connected to a voltage, and then I need to use a coupling capacitor. So in this case, I am assuming that I cannot connect it to a DC voltage or current. So I am using a coupling capacitor here. And the size of the coupling capacitor naturally will depend on the bandwidth of interest. So it may be that it needs to sit outside of the chip, or there might be different situations there. So in this case, I put this coupling capacitor, and then I will check if the circuit works. So let's go to cadence, and then let's check this biasing step. Okay, so let's make it a bit smaller here. So I run it. We notate the DC voltages, notate the operating points. And let's take a look first here. So the presence of these capacitors at the input will naturally filter the signal at low frequencies. It is high pass filtering the signal at low frequencies, and then it will let pass higher frequencies. So the size of that capacitor has to be decided based on which is the minimum frequency that I should handle. And then we see that the gain is the same at higher frequencies as we expected before. The same as before, and the position of the poles and zeros has not really changed. The position of the poles at high frequency has not changed, but I have the zero and a pole at low frequencies that are this high pass filtering. Those are here. The pole and the zero here. Now I cannot do anymore the static linearity test, because I have just breaking the signal path for DC. So the static linearity cannot be checked at this point. Okay, then I do a quick check on the biasing, and then we see that the transistor is biased at 20 microamps as I expected. VGS is correct, 437 millivolts. VDS has changed. Now it is 437 millivolts, so it has been reduced from before. And now I have to check. Now it is important to check, because if I cannot tolerate VDS of 437 millivolts because of the linearity requirement, if my signal swing it is let's say larger than 300 millivolts, then VDS here will be pressed very close to leave the saturation region. I mean, remember that for weak inversion we need around at least 4 thermal voltages, so that is above 100 millivolts at room temperature. So this particular configuration will be limited to around 300 millivolts signal swing here, and most probably will get degraded under corner conditions. So there is no much margin for 300 millivolts here. But for instance, if the signal swing is 200 millivolts, that will probably be okay. But I really have to check. Now, if the signal swing it is 400 millivolts, this will not work. There will not be margins here, and the signal will clip for low voltages. When the output voltage is low, it will just be clip. So yeah, if the signal clips, then I cannot use the feedback loop to bias to set the gate to source voltage of this transistor. Okay, so then I need to do something else, but we will take that a little bit later. Now let's assume that the output signal swing that I need it is lower. It's let's say around 200 250 millivolts, then this is okay, this will work, and then I can continue with the implementation of the current source here. So then we go to the next step. So the next step will be to implement this current source that we need for bias or amplifier. So this current source has been implemented here by using the current mirror, and yeah, the current mirror that we see here, it is formed by this transistor and this transistor here. The current mirror needs reference current, and this reference current is expected to be very stable and very precise. And normally an amplifier has an input for this current reference that most of the time it can come from another current mirror. For instance, the current mirror that we have here. This current reference is derived from a bandgap reference that basically produce a voltage reference that it is relatively constant over a large temperature range. So we use this block to derive a current that is also independent on temperature. So normally it is small current because we don't want really that the biasing consumes a lot of power. So we make it a small current as a reference, and we are mirroring this reference current to in this case from transistor M4 to transistor M3, and then from transistor M2 it is mirrored again to transistor M1, that it is actually our current source. And then we can use different sizes of transistor in order to amplify the reference current, at the small reference current, to the value that we need. That in this case it is 20 microamp. One thing that it is very important, it is that the current mirrors are extremely noisy. So we might have to filter the noise that is coming from the current mirrors. So this diode connected transistor, for instance, will produce a noisy current here, and depending on the ratio of the sizing of these devices, it might be amplified, and then this current also will be mirrored and amplified again. So I have to be careful when I use current mirrors, because the noise current get amplified by the current mirror. So one thing that I can do, and it works very well at high frequencies, is to add the coupling capacitors. Okay? I can add the coupling capacitors in parallel to the diode connected devices. So the diode connected device has a resistance of around 1/GM, and then I put this 1/GM in parallel to the coupling capacitor here, and then basically it will produce a pole. It will work as a low pass filter, and it will filter high frequencies. Notice that for the PMOS transistors, my target it is to decouple the gate and source of the devices, so I connect the capacitors between the gate and the power supply, VDD. For the NMOS devices, my target it is to decouple the gate and the source. The sources are connected to ground, so I put the capacitors from gate to ground. Extremely important when I am designing current mirrors is the output resistance of the current mirror. We have used ideal current sources until now, and now I have to guarantee that the resistance of the current mirror it is much larger than the resistance of my amplifying devices. In this case it is M0 here, and then it is not only the resistance that it is going to affect the performance. The the current source, the implementation also come with capacitances. So I should expect that the capacitances that are present in the current mirror will also move the poles and zeros. So I might need to adjust the compensation. Okay, so there will be a shift more in the position of the poles, but it also will change a little bit the loop gain, because now I am placing this impedance in parallel to my amplifying device, so I should expect that some of the loop gain will be lost. Okay, so when we put these devices, we need to test. So before leaving this one, I have placed a capacitor in parallel to the power supply, and although it is not really part of the biasing step, it is good to mention that the power supply itself, it is not ideal. It may come with noise. It may be VDD coming from a switching power supply, or it may be coupling noise from other stages. There may be digital noise coupling also to the power supply. So whenever possible, and you will want to add a decoupling capacitor in your block, so a capacitance that it is basically filtering this high frequency noise. And whenever you have a space in the layout and you have to fill some holes, typically you will be adding some capacitance, decoupling capacitance to the power supply, just to improve the filtering of noise in the power line. So let's take a look our circuit. So we have our circuit here already implemented with the biasing implemented. So we are going to open the ADL and run the same simulations that we have been running to confirm that the performance of our amplifier is correct. So now we are going to, let's run it. Notice that now I cannot anymore run a DC sweep. No, we have a capacitor here, so it is preventing me to run DC sweeps anymore. So, but I can run anything else, including transient simulation. So I can already test this component, this amplifier with large signal simulation in time domain. So, but for now we are just going to try the DC, noise AC, and pole zero to see if something has changed. And then okay, we have just run the simulation. Let's have a look to the DC operating point. Annotate it here. DC node voltages, DC operating points, and then we can see that we bring 1 microamp. This 1 microamp has been mirrored with a factor of 2 to this second branch. Now it is 2 microamps here, and from this branch to the transistor that it is connected directly to the amplifying stage, it is around 20 microamps, so it's a factor of 10. So from the input current to the output current, I have a total factor of 20. So think about this, because if there is a factor of 20, the noise of this transistor will be multiplied by a factor of 20. So I have used this capacitor here to filter the noise of this diode connected transistor, and this capacitor here to filter the high frequency noise of this transistor. The DC operating point, it is correct. So now let's take a look to the other performance metrics. So we take a look to the gain, and this has not changed. It's around 94. kilo ohms. And let's take a look to the position of the poles and zeros, and for that I will bring the zeros in the same plot, and then let's bring these ones here. And then we can add we can add some markers. So these poles are located almost in borderware position, so they are okay. Now let's look here. Here we have a bunch of poles and zeros that are superimposed, meaning that they are just canceling. This is what the pole zero simulation found, so they don't really matter. So, and we can see here that the at very low frequencies what we have, it is just a zero and a pole. So there is a zero located at the origin, and then a pole coming at around 1 kilohertz. And this one, it is coming from the capacitor that is the coupling here. So that is giving us the high frequency, high pass filtering. Okay, so and then the last thing to check it is the noise. So it is very important to check that the noise contribution from the biasing is not degrading the performance. So I'm going to check the integrated noise voltage. Let's see from very low frequencies, and let's take very large band. So I have simulated up to 100 meg. Yeah, so let's take it until 100 meg, and then I include all types and 10 first contributors, and then we take a look here, and okay, we can see that from the noise contributor list, the first noise contributors are the feedback and the source resistor, as I expected. Then the transistor, we have M1, M0. Sorry, the first contributor comes from M0. That it is the amplifying device, the common source device, which it is correct. This has to contribute with most of the noise, and then I see that the noise contributor of the noise contribution that comes next, it is the current source, and it has considerable noise contribution, is around 8%. So I expected this also, because this is basically forming part of the input stage, so it will have some noise contribution. The noise of this transistor will add to the output, but there are some strategies to reduce the noise of this transistor in case it is needed. One, it is to reduce the transconductance. So the transconductance of this transistor has to be lower, the transconductance of this transistor, so that the noise current power density reduces. Remember that is 4 kT lambda gm square, so lambda gm. So I reduce the transconductance, and then the noise contribution of the transistors will go down. So I have this possibility. On the other hand, reducing the transconductance here might reduce the output impedance also, so it is a trade-off that I have to do. But there is a room for improvement if it is needed. And then let's see, after transistor M1, it is transistor M3. Search for transistor M3, where it is. We have transistor M3 is here, and it is contributing around 1.6%, so it is very little. So, but think about this: this transistor has been connected as a current mirror here, and the noise of this transistor is actually multiplied 20 times, but it is filtered by this component. So let's do something very interesting now. Let's just disconnect this capacitor. Let's save it and let's run it again just to see what is the impact of the noise. So we have oh, something also interesting to see. I disconnected that capacitor and then I have moved a little bit the position of the poles also here. Sometimes I have to be careful with the current mirrors because they can move the poles and the zeros and make the circuit unstable. It doesn't look like this is the case here. So let's take a look to the noise. So let's see results, print noise summary. We apply, and then without the decoupling capacitor, I can see that M3 it is adding 5.7% of the noise. Okay, so it started adding a little bit more noise. Before it was 1.53%. So whenever possible, it is good practice to try to filter those noise sources. Okay, so I put it back here and I bring it back, this one. Okay.